Okay, so solving this Lagrangian or the constraint optimization problem that we defined in the previous slide actually results in very interesting or very promising theoretical results that guarantee monotonic improvement in our policy over iteration. So our policy must improve over iterations. Specifically, they prove that the performance under the new policy must be greater or equal to the loss, the important sampling loss, when we consider the previous policy, for the new policy over the previous policy, minus C, some kind of a constant, multiplied by the KL divergence, the maximal KL divergence over all the observed states, or over all of the states in the state space, reachable states. Where specifically J of the policy that is defined by the tunable parameters is the expected sum of discounted return. Right as before, this is the same J. C is defined as 2 times epsilon over gamma, 2 times epsilon gamma times gamma over 1 minus gamma squared. And specifically when epsilon is defined as the maximum advantage over the old policy over all of the states. We won't go over the entire proof. The important thing to understand is that it does provide us with monotonic improvement guarantees under some assumptions that we are able to compute these values over over the entire state space, which is a bit of a strong assumption. We'll drop it in a second. So the optimal point in our trust region is guaranteed to improve the policy with respect to the expected return over the previous policy. Okay, as before, if you go and read the paper, you're more than encouraged to do so. You will see that the greater equal sign here becomes a lower equal sign. Again, this is because they consider, in the original paper, they consider costs instead of rewards. Usually you want to minimize costs and maximize reward. Okay, so now we can define the TRPO algorithm, and for each iteration, we run our policy for t time steps, or n trajectories and episodes. We estimate the advantage function at all time steps, and then we maximize the important sampling loss, subject to our trust region constraint, over the KL divergence. Now you'll see that in the original TRPO algorithm, trust region policy optimization algorithm, they take the mean and not the max, right? Previously I showed you that the theoretical results hold for the max over all of the states, and here they just take the mean. So it's important to say that the monotonic improvement guarantees, theoretical guarantees, hold only for the max version. But in practice, doing the max version is very problematic. You can't go over the entire state space. And also, just taking the max over all visited state is usually an overkill. It gives you too big, it's hard to bound the max value. So in practice, bounding the mean value works better, right? Specifically as maximum is too conservative. It's correct theoretically, but it's practically it's better to take the mean. Okay, so how do we solve the KL penalized problem? We need to do some estimations there. So we would like to maximize the important sampling loss minus beta times the average KL divergence, right? What we do is we use linear approximation for the loss function and quadratic approximation for the KL divergence. And now this results in maximizing G, which G is just the policy gradient, L over the gradient in L over the policy, between the two policies that we have, the old policy and the new policy, minus beta over 2 times, again, the difference between the two policies, times the Fisher information matrix. Okay, this is the second order derivative matrix of the KL divergence with respect to the policy. And again, we'll take, as we've seen before, we discussed the Newton step direction. In this case, it will be the inverse of the Fisher information matrix multiplied by G, which is the policy gradient. This is also known as the natural policy gradient. So now we can define TRPO as a general policy gradient algorithm, right? The general approach as we've seen before. Now we use a linear and quadratic approximation plus penalty. This results in the natural gradient algorithm. If you can see now that if we set no constraint, that is, we set the KL divergence bound to infinity, we don't care how far they are apart from each other, then what we have is practically policy iteration. That is, the new policy is updated to be the best one-step policy over state visited during the previous policy. Right? This is the policy iteration algorithm as we've seen before. We don't care how far we jump, but we just, from our current policy, the step size, we just approximate or try to find the best policy given our current advantages, our current values. If we set our constraint using Euclidean distance between the two, the old and the new policy, instead of KL divergence, this will, you can plug it in and see that this will just correspond to a constant learning rate. That will be the basic policy gradient algorithm that we've seen before. Okay, so let's review the TRPO approach that we've seen so far. In TRPO, we optimize a surrogate loss, either the PG loss, the policy gradient loss, or the important sampling loss. They are the same, right? They are the same thing. These are the loss that results in the policy gradient, right? Working backwards. We had a constraint in the form of a bounded KL divergence. And then, if we use linear approximation for the loss function and quadratic approximation for the KL divergence, we do Taylor approximation on the Lagrangian that is composed of both of these, using linear and quadratic approximation for each one of these terms. This will correspond to the natural gradient step, the inverse of the Fisher matrix times the gradient, the natural gradient, the policy gradient. And this will allow us to perform natural gradient descent step. We can approximate the Fisher matrix relatively fast using what's called conjugate gradient, and this can be seen at this citation here. However, the Fisher matrix can be very, very big, so it's the number of tunable parameters in your policy squared. Okay, so this can be very, very big, specifically if you have a policy which is a deep neural network, right? A very big or a deep policy network. So we might want to avoid computing and so mainly storing and working with the Fisher matrix.